Hi, I'm Andrew Holder. I'm from the Faculty of Informatics, and more specifically I'm in the School of Mathematics. I'm here to talk about the mathematics of juggling. Now, maths can be applied to virtually everything. Probably a lot of people are told this, but they never really believe it. A good specific example of this is juggling. Now, juggling is one of those sorts of fun activities that maths can be applied to, and the maths was originally created by graduate students instead of doing their actual work as a way of coming up with new and interesting patterns that they can juggle. So we'll go over what we mean by juggling, and then we'll look at the actual mathematics of it, which is the stuff to do with juggling sequences. So the first question will be, what do we mean by juggling? Juggling can mean various things. It could mean juggling your social life and work, it can mean juggling responsibilities, but we're referring to the act of just juggling a number of objects in the air, one after the other, catching them in a repeating pattern. So we first need to assume something. We assume that a ball will get caught and thrown at the same point in time. So if you catch a ball, it's then the next one to get thrown. So that's an important assumption. Now we'll go on to what we actually mean by juggling. So we'll define juggling. So the first point in our definition is to say that balls are juggled to a constant beat. So they're juggled at discrete, evenly spaced moments in time. So if you watch me juggle, the throws roughly occur at the same sort of distance apart time-wise. So that's the first thing we assume. Okay. Second thing is that patterns are periodic. So our patterns will occur and then repeat. So it just keeps repeating. We also assume in that the juggler has been juggling forever and will never stop juggling, repeating that same pattern over and over again. So the third point, and this is a very important point because this is where most of our juggling patterns come unstuck, is that we assume that at most one ball gets caught and thrown at any point in time. So if one ball is caught, that ball is then thrown. You can't have more than one ball thrown, and you can't have more than one ball caught on any one beat. So now with that definition out of the way, we can move on to the math. So we look at juggling sequences. So this will look at some patterns, the sequences, some diagrams, and then something known as the average theorem. So if you watch a juggler, you notice the juggler will swap between hands on alternate beats. So you can think of odd beat throws as right-handed and even beat throws as left-handed. Each pattern will require throws of varying heights with a specific number of balls. Now, we define what we mean by height. When we talk about height, we don't actually mean the physical height that the ball goes. The height, as you can see here, is a measure of the number of throws that occur before a ball will be caught and thrown again. So we've got an example of a height of 3. So if you watch this pattern, I'm actually throwing the green ball a height of 3. So you notice that it will get thrown, then the white and yellow ball gets thrown before the green ball gets thrown again. And so we say that that green ball is getting thrown a height of 3. So an important note about the heights is that odd height throws will throw to the alternate hand, and even height throws will throw to the same hand. So say for example you threw a ball a height of 3 from your right hand, it will then land in your left hand when it eventually did land. But say I threw a ball a height of 4 from my left, it will then land in my left hand when it eventually did land. So that's the difference between odd and even height throws. What would a height of 0, 1 or 2 look like? Now these are 3 very interesting throws. Now if you think about a 0 is saying that you're throwing a ball no height. So it's saying that a ball would go nowhere. So the only way that you can possibly do that is if you're not actually throwing one, and it's kind of just a ghost throw. So you can display this. So I'll display this in a pattern which would be called a 3-3-0. So watch my empty hand during the pattern. So you'll see that I'm actually incorporating a throw when nothing gets thrown and nowhere goes. So it's almost kind of like a pause in the middle of the sequence. So that's what we call a 0. Now the next one's a 1. So this is another special throw. So this is a throw where it just travels for one beat. So that means it will get thrown from one hand, and then because it's traveling only one beat, that means it's going to land in the next hand on the very next beat where it's ready to be thrown again. So a pattern where this is displayed is a shower where everyone tries to learn at first, which is actually probably going to stuff up a few jugglers, but I'll display this. This is what's called a 3-1. So it's just where you're doing the cross in the middle, and you notice that it crosses across and then it's the next ball to get thrown. So that's a 3-1. It's incorporating the 1. That's the one that's just getting passed from one hand to the other. Now a 2 is another special throw. If we think about what was already said about odd height throws and even height throws, we know that a 2 should land back in the same hand which it was thrown from. Now because it's only travelling a beat of 2, say we threw the ball a height of 2, that means it gets thrown, it's up in the air for 1 beat, where another ball will get thrown whatever it's going to do from the other hand, at which point we then travel back to the right hand, and where 2 beats have passed, so that ball would then land back in the hand, that one that we just threw a height of 2. So it means it goes up and comes back down into that same hand before any other ball lands in that hand. So that means that that ball, you can just sort of hold it. That's what will actually happen when you see a 2 displayed. People just hold the ball. And so this is a pattern where the 2 will actually occur. So if you watch the balls, you'll see that one of them will actually sort of just stay in the one hand as a pause while there's 2 consecutive throws occur from the one hand. Well, that's actually because we're technically throwing a height of 2 in that hand. So that's what a 2 does. It's just nothing. So we now move on to the maths of this. So we needed some way of representing the pattern mathematically. So the way we do this is we represent a pattern by the height of its throws in the order that they occur. So say we have a juggling pattern where it's got throws at 4, 4, 1, that means we just write 4, 4, 1. And that's how we represent that particular juggling pattern. The number of throws in a pattern is known as the pattern's period. So in the case of a 4, 4, 1, there's 3 throws in it, so that means it's got a period of 3. Now we also have that same pattern, that 4, 4, 1, could also be represented by 4, 4, 1, 4, 4, 1. So that would have a period of 6. Now a sequence is minimal if it's the shortest possible sequence that can represent that juggling pattern. We now have a little note on the height. It's convention to represent throws higher than 9 by letters starting at A equals 10. Now this is done to avoid confusion. Take the example of a throw a height of 11. That could be misinterpreted as 2 consecutive 1s. So that's why 11 is represented by a B. Now this brings us to an interesting point. This suggests that you possibly can juggle words, and there's quite a few interesting words that actually can be juggled. One of which is proof and theorem, which mathematicians love, and hopefully you guys will understand that if you do a little bit more maths. So we now need to have a method to find out if you can actually juggle all juggling sequences. So a good way of doing this is a juggling diagram. So the way you represent a juggling diagram is by drawing a number of beats one after the other, as you can see up here on the screen. So I've got odd beats in black and even beats in white. You don't have to do that, but it's just something I've done here to make it a bit more clear. And on this, we'll draw our pattern. So we're going to consider the pattern 4, 4, 1. So you'll notice I've got the 2 throws already coming in here. So I've got a blue coming in one and a black line representing a throw that's coming in. Now if you look at the first black dot, that's what we're going to consider our first throw from. So we've got a sequence 4, 4, 1. So it means we're going to have to throw our first ball a height of 4. So it's going to travel across to the right 1, 2, 3, 4 beats, at which point it's going to land back down, and you can see it landing back down on a particular black dot, at which point on that beat that ball will then be thrown again. If we then move across to the next beat, we'll then have to throw another height of 4 because that's the next number in the sequence. So it gets thrown another 1, 2, 3, 4 beats to the right, at which point it will land again. And you can see it's landed the beat after the red one lands. We then go across to the next throw, which is going to be a height of 1. So because it's just a height of 1, it's just going to travel 1 beat, at which point it will land again. So at that point, that ball will then be thrown again. At this point, I'll just make a little note here. Note that I've got a few different patterns or a few different colors here for the lines. So a red one, a blue one, and a black one. That becomes important. I'm actually tracing out the path of each individual ball here. All right, so back to the diagram. We've gone through our sequence 1 full time. So we've gone 4, 4, 1. So because we've gone through every number, we just cycle back around and repeat. So we then throw the next ball a height of 4. So that's that black one that was just thrown, because it's just landed, it then gets thrown again. So it gets thrown a height of 4. We then go across and then throw the next ball from the next beat, it gets thrown a height of 4, and then our next throw was a 1, so it then gets thrown a height of 1, and we draw that line in. And then you just repeat that. So from this diagram, which we've got completed now, we can see that this pattern is viable as there are no throws being caught or thrown at the same point in time. So this is a viable pattern. It suits our definition. So I mentioned that we had a few different paths of the balls there. So I noted that we had the path of one ball shown in red, the path of another ball shown in black, and a path of another ball shown in blue. So these each represent what's known as orbits. Each ball will trace out a particular trajectory, so it will trace out a particular path. And the number of paths, or orbits, has to equal the number of balls. So this is a way of determining the number of balls that is required for a particular sequence. So we can see here in the instance of this one that it has 3 orbits, therefore this sequence will require 3 balls to juggle. Now let's look at some of these sequences with a juggling generator. So this is an animator that will allow you to see what particular juggling sequences will look like. So here we've got a juggling generator. So a good sequence that we should probably look at, which we've mentioned a few times, is the 4-4-1. So if you just type in 4-4-1 into the generator, then hit enter, it will actually start doing the sequence for you. So you can see here it's tracing out what's called a box pattern. So this is what the typical 4-4-1 looks like. Now this will also show us if certain patterns don't work. So say I type in the 3-2 again, it will give me an error. Now this particular generator is quite good because you can actually use it to generate particular patterns. So if I go to show the controls, say I want a pattern that contains 4 balls with a maximum height of 6 and a period length of 3, I then set those controls and then I generate, and it will generate all possible patterns that do that. So if I click on this 5-5-2 and hit return, it will then start juggling that sequence for it. So see how this has got a 5-5-2, it's got the 2 in it. You'll notice that the pattern is doing a pause now and again, and then the other balls are going a height of 5. So this pattern is got a period of 3, it's got 4 balls occurring, and it's got a maximum height of 5, so that's less than 6. So that's met the conditions of our generator. So you should have a bit of a play with this to see what sort of patterns you can figure out. Try typing your name, that's always fun. Unfortunately, my name isn't juggleable, but we'll now go back and have a look at the rest of the presentation. It can be a tedious task to have to draw a diagram all the time to determine the number of balls required to juggle a particular pattern. So that's where I'm going to introduce the average theorem. So the average theorem states that the number of balls required to juggle a sequence is the average of the height of the throws. So if we consider the sequence 4-4-1, the average of that is 4 plus 4 plus 1, so that's equal to 9, divided by the number of throws, so divided by 3, that's equal to 3. So that tells us that we require 3 balls to juggle that pattern. And that's the same as what we got by looking at the orbits and also when you look at the juggling generator. This then leads us into what's known as the average test. So this is a method of determining if you can't juggle a sequence. So that's an important distinction there. It doesn't tell you if you can juggle a sequence, it only tells you if you can't juggle a sequence. So it states that if the average of a non-negative sequence of whole numbers is not a whole number, then that sequence is not a juggling sequence. So if we consider the pattern 3-2, we have the average of that is 3 plus 2, so that's 5, divided by 2, so that's equal to 2.5. Since that's not a whole number, it's therefore not a juggling sequence. So I hope you've learned something about juggling here and how maths can be applied to it, and go have fun.